So for strings, let's just go over kind of the theory first of all. So let's say I have a string, and I were to send a wave pulse down it. Okay, maybe it looks like that, right? So I'm going to send a wave pulse down it. So that wave pulse is going to head down the string. It's going to hit the end, and what's going to happen to it? You guys remember we did this demo yesterday? What happens when the pulse hit the end? It goes back. Yeah, it reflects. We say use the word reflects. It reflects backwards. And I don't know if you remember this, but when it hit the end, it actually inverted upside down like this. So this one came in this way, and it actually inverted. And when it hits the other end, it would invert again, and it would come back and forth. So if there was no friction, this would just keep going up, down, up, down, up, down, infinite forever. Well, what would happen if I sent, say, multiple pulses? Say 3. 1, 2, 3. Well, as each one hit the end, it would reflect. Right? And sooner or later, these three are going to go this way. They're going to invert on top, and they're going to invert and back and forth and back and forth. And they're going to start interfering with each other. So you're going to have some on the top, some on the bottom, others on the top, and others on the top, and so forth and so on. And you're going to get all this chaotic interference. And in fact, this interference pattern, if these are not nice frequencies, as we'll soon learn, you would get a crazy, chaotic interference pattern, okay, with no necessarily rhyme or reason to it. It would just be chaos. And you saw this a little bit yesterday when I was sending in all the pulses. There wasn't necessarily a nice pattern that emerged. And I'll do this a little bit later with some demos also, so you can see it. So anyway, this would be what this kind of looks like. However, if you send in a perfect frequency, so if you find the absolute perfect frequency, what will happen is as the waves start to reflect back and forth, they'll get this nice interference pattern, this nice pattern of constructive and destructive interference that that looks nice, okay? And as you'll see, the pattern looks really nice. And so we call this is what we might call a state of resonance. And we can kind of call this kind of this special frequency, or maybe perfect frequency. That produces, I'm going to write the word nice, interference patterns and we actually will use the word standing waves. So probably from this point forward, I'll just kind of refer to this either as resonance or standing waves. And so these are these nice patterns where the waves almost look like they're standing still. It looks like a snapshot of a wave as you look at it and visualize it. Okay, so that's what we'll be focusing on for the next few days. And you know, when you're playing music, that's what you're looking to get, is to find these special resonance patterns. So let's start with the easiest one. The easiest one is what we call the fundamental harmonic, or the first harmonic. The fundamental harmonic, or the first harmonic. And the fundamental harmonic, if you were to play guitar, the fundamental harmonic is what you would see. This is the easiest one to get. And if you were just to naturally pluck a string, this is what you would end up seeing. If you were just to hit anything, everything has, not just strings, everything has these fundamental harmonics or states of resonance. If I just hit a tuning fork, for example, it would vibrate at its fundamental. So anyway, it looks like this. And I'm sure you've all, at one point at least, if you're not a musician, you've at least plucked a string, plucked a guitar string or a bass or a violin or something. So it looks like this, and it's actually kind of oscillating back and forth, back and forth. So it's not truly standing still, but we still call them standing waves because they kind of look like they are. So some of the fact features of this, these points right here are what we call nodes. And these points at the end are what we call antinodes. So actually I wrote antinode twice, but really it's just this location is the antinode. So we just say there's one antinode. And nodes would be where you get this perfect destructive interference, where you get full cancellation. Antinodes would be where you get that maximum constructive interference, so you get the highest possible amplitude here would be at the antinode region. Now one of the nice things about these is this. Remember, this is just a string, and so a string has a length to it. And if you look at my picture, you should notice, well, this is either a wave or a portion of a wave. So look at this picture here. Do you notice how much of a wave this encompasses? A half of a wave. Good. Does everyone see that? It's a half of a wave. I mean, if I draw, let's just draw a real wave over here. This would be a full wave, right? And notice how much of this wave do you see? We start right here and we end right here. So that's like a half of a wave, right? A half of a wave. So the nice relationship is that the length is equal to 1/2 of a wavelength. So length is equal to 1/2 of a wavelength. Okay, so that's our fundamental, our first harmonic. Let's look at our second. So our second harmonic is going to look like this. Now remember, the length is still the same. It's still the same string. What you get with the second is a picture like this. Okay, and this one kind of oscillates up and down. And again, I'll do this demo for you in a few minutes. This one kind of oscillates back and forth. Kind of alternates, would look like this. What you should notice is right in the middle, this would be our node. We still have the nodes on the end, but this would be our node right in the middle. And so right here there's no vibration at all. In fact, if this was like a string, a guitar, if you were to put your finger right in the middle, it wouldn't move. It would just stay there. Okay, there'd be no vibration there. Right here we have our antinodes. How many antinodes do we have now? 2, 1 there and 1 there. Okay, so remember this string still has a certain length. How much of the string do you see? Or how much of a wave do you see? The whole thing. Good. So if you picture your wave, here's our full wave. That's what you see, a full wave. So that's nice. We just say the length is equal to the wavelength. So for the second harmonic, the length and the wavelength will be the same. Alright, let's do the third. Now you can have many harmonics. You can have 3, 4, 10, 50 harmonics. Okay, we're just going to do 4. I'll do 4 for your notes, but you should notice some patterns that happen, and you should be able to figure out the various harmonics on your own. Okay, so we're going to just, remember the length of the string is the same. As you move up in harmonics, you're just going to add a node and add an antinode. So this would look something like this. So we now have 1, 2, 3, 4 nodes. And 1, 2, 3 antinodes. Notice the number of antinodes exactly equal to the name of the harmonic, first, second, third. How much of a wave do you see here? Okay, 1.5, right, or 3 halves. So notice here's a full wave plus an extra half. So we can say L is equal to 1.5 lambda, or we could say 3 halves lambda. Notice what's happening as we move up in harmonics, what's happening to the wavelengths. They're all changing by 1/2. And what's happening to the, is it getting longer or shorter? Shorter, good. So this was only a half, remember, so the full length would be twice, the full wavelength would be twice. This is L, and this would be 2/3 L, so it keeps getting smaller and smaller. Okay, let's do the fourth. Actually, see if you can draw the fourth by yourself. See if you can notice the pattern. I do want you to be able to reach the point where if I say the 8th harmonic, what does the 8th harmonic look like? And you could draw it out, you could find the relationship. Okay, so you should have 4 antinodes and 5 nodes. Okay, so take a look at your picture. If you got the same thing that I did, great. If you didn't, then fix it. So that's what your picture should look like. How many waves do you see now? 2. So notice every time it goes up by a half here, right? The length relationship. So 1/2, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, etc., etc. Okay, alright, so the next thing we're going to look at is speed. So the speed down a string is different than the speed of sound. Remember, the speed of sound is the speed in air, okay? But this, the speed of like the air molecules, this is the speed down a string. So let's look at the factors that would affect this. So speed in a string, or velocity, I guess, probably be a better word. And so the equation for this, for those of you that have ever tuned a stringed instrument, what do you do to tune a stringed instrument? Okay, you tighten the knob, and what's that doing? Okay, changing the tension. Good, so you're changing the tension. And really, by changing the tension, what you're doing is changing the velocity. And if you look at our equation, v equals f lambda, lambda is just dependent on the length of the string. If you change the velocity, if you increase the velocity, what should happen to the frequency? Should increase, right? So if we tighten it up, or if we increase the tension, so I'll write this as f sub t, f sub t would be the tension in the string. If you tighten the string, what you're doing is increasing the velocity down the string. By increasing the velocity, you would also increase the frequency, so higher pitched. Okay, tighten it up, the pitch goes up. Okay, and then there's one more factor. If you've looked at a guitar, right, you guys have all done that. There's 6 different strings. What's the difference between the different strings? Thickness of the string, okay? Or more specifically, the mass of the string is different. So the other factor is the mass. So if you have a heavier string, would you expect the velocity to go up or go down? Down, yeah. The heavier the string, the smaller the velocity. So we're going to divide this. Now, it's not going to just be the mass of the string. It's going to be the mass over length, m over L. So if you think about it, like you could have a string from here to New York. That's going to be a pretty heavy string, right? If you had a piece of thread from here to New York, even though it's a piece of thread, it's still going to be pretty heavy. So it's not just the total mass of it, but the mass over length, or what we call mass density. So it's more about, say, the thickness of it, but how heavy per meter, so the kilograms per meter of the string. That's going to tell us, essentially, that's going to change. So the greater the mass density, the smaller the velocity. Okay, so that's our V first string. Oops. All right. So let's go ahead and let's pause, or